To the video on geometric arguments and proofs using vectors. Okay, so to get us started with this video, we have a triangle here and it has the vertices O, A and B. So triangle O, A, B. And as we can see, we've got two vectors. So the vector from O to A, so we draw that like this, or write that like this, so O to A, the vector there is A. And then the vector from O to B, so we write that like this, O to B, that is the vector B. So what we're going to do here is we're just going to have a play around with this. And we're going to look at other vectors and other paths that we can define. So the big problem we've got at the minute is we haven't got a vector AB. So we've got this problem, so we've got AB. But we haven't got a vector that defines that. So we don't know what AB is at the moment. But we can work that out and we'll come back to that at the end of this example. So, going back to OA. So O to A, so starting here and ending up here. Let's just get a highlighter here actually. So we're going from O to A. So that travels along the vector A. But what about A, O? So what about if we want to go from A to O in that direction? Well, it can't be the vector A because that's in this direction. If we want to go this way around, well then it's got to be minus. So that would be minus A. And similarly, if I said to you, well, what is B to O? Which we draw like that. Well, we'd look and we'd say, well, O to B was the vector B, but we're not going in that direction from left to right, we're going from right to left, so it must be minus B. So like that. And knowing both of those things is going to help us. That's going to help us find the vector AB. So that's the point really. So we've got this problem that we don't know what AB is, because there isn't just a path defined down this line here that is AB. So we've got to use some algebra and our knowledge of vectors to help us work this out. Well, AB, well that's the same as going from A to O and then O to B. So we've got to go a slightly longer way around because there isn't a vector that defines this path. So we go A to O and then O to B. So we go A to O like that, plus O to B, like this. Well, A to O, well we know that that's minus A, it's the vector minus A, so that's perfectly fine, we're okay there. And then we know to go from O to B is the vector B, so we add B, like that. So we've sorted out the problem of going from A to B. What about if I then said, what's B to A? Well, we look at our diagram, so we go from B to A. Well, again, there's not a path defined, but we could go from B to O and then O to A. So we go from B to O, and then we've got to add O to A. Well, what was from B to O? Well, from left to right it was positive B, but we're going in the opposite direction, so it would be the vector minus B. And then O to A, well that was just the vector A. So we're adding A. So that would be the vector B to A. As you can see, A to B and B to A are opposites of each other. And we would expect that, because when we looked at this example here, if we were going from O to A, it was a positive A, and if we're going from A to O, it was a negative A. So we would expect that. So what we're going to do now is we're going to look at some more examples, and then we're going to apply our knowledge to some harder questions later on. Moving on from the triangle that we've just started with, we've now got a trapezium. So this trapezium is the trapezium ABDC. So A to B is defined by the vector A, B to C is defined by the vector B, and then D to C is defined by the vector 2A. So just going back to a video on a previous point, notice that this is a trapezium. So A and AB, so the line AB and DC are parallel. AB is the vector A and DC is 2A, so it's two lots of the vector that defines AB, which we expect, because what you should know is that vectors that are parallel are scalar multiples of each other. So A, and then to get 2A we times by 2, so that's why it's 2A, just on a side note. Okay, so we want to find the root BA to begin with. Well, A to B was A, so B to A will be the opposite, so it's minus A. Then question 2, A to C. Well, A to C, well that's the same as going from A to B and then B to C. So writing that out, it's A to B plus B to C, like that. Well, A to B is the vector A, and then B to C is the vector B, so just add B. Then we've got D to B. Well, what is D to B? So it's D to C, and then C to B. So that's the route that we take to get from D to B. So again, I'll write that out. So that is equal to D to C plus C to B. Well, D to C, that's the vector 2A, and then C to B, well, that will be minus B. Why is it the vector minus B? Well, B to C was positive B, so if we do that route in reverse, so C to B, that will be minus B. And then finally, we've got A to D. Well, we can't go that way because we don't have a vector that defines A to D or D to A. So we can't go that way, so we've got to find an alternative route. What will that alternative route be? Well, we could go from A to B, then B to C, and then C to D, like that. So again, I will write that out. So we could go A to B, plus B to C, plus C to D, like that. Well, A to B is the vector A, so that's easy. B to C, well that's the vector B, so again that's easy. And then C to D, well if we know that DC is 2A, then C to D will be minus 2A because we're going in the opposite direction. So we can then add the vectors up there. have the same letter. So we've got a minus 2a, well that's minus a, and then we're adding b to that. So it's just like algebra really there. So we've got a minus 2a, so that was minus a, and that would be better really if we wrote b minus a, like that. And there we go. Okay, so here we have another trapezium. And this trapezium is w, x, y and z. So the route from w to x is defined by the vector b, z to w is defined by the vector a, and then z to y is defined by the vector 2b. So our first question is to find z to x. Well, z to x, so we start at z and we go to x. So we go z to w, then w to x. So I'll write that down. So we go z to w plus w to x, like that. Well, z to w is the vector a, and then w to x is the vector b, so plus b. So that's that sorted. And the second question, we've got y to w. So to do that, we go y to z, and then z to w. So y to z, and then z to w. So y to z plus z to w. Well, y to z, that's going to be minus 2b. Why is it minus 2b? Well, we know that z to y was 2b, so if we go the opposite direction, so in reverse, that would be minus 2b. And then we've got z to y. Well, z to y, sorry, z to w, and z to w is a, like that. So y to w is minus 2b plus the vector a, which would be better really if we wrote a minus 2b with the positive vector first. Then we've got the route x to y. So x to y. Can we go that way? Well, no, because we don't have a vector that defines that route. So we've got to find an alternative route. So that alternative route will be x to w, w to z, and then z to y. So it will be x to w plus w to z plus z to y, like that. Well, x to w, that's going to be minus b. Then w to z, well again, that's going to be a minus, so it will be minus a. And then z to y, well that's positive 2b. So then we can add our vectors for b together, or in this case take away, and then we've got nothing else for a. So we've got minus b plus 2b, well that's just 1b, positive 1b, and then minus a, like that. So that's that sorted out. And then our last question is x to z. Well, what is x to z? Well, it's x to z there. So that written down algebraically, that's going to be x to y plus, x to w, I've done that twice now, and then w to z. Well, x to w, that's minus b, and then w to z, well, that's minus a. Our examples are building steadily. So we have the shape A, B, C, D, E, F. F to A is defined by the vector B. A to B is defined by the vector A. E to B is defined by the vector 3B. D to C is the vector 2B. And E to D is the vector A. Okay, so our first question is to find a vector for F to E. Well, like we've done before, F to E is this line here. We don't have a vector that defines that, so we're going to have to find a new route. So that route will be F to A to B, and then B to E, like that. So again, I'll write that out. So it will be F to A plus A to B plus B to E. And we know that this will give us the correct answer because we start at F and we end at E. Yep. So it's just a case of writing in our vectors now. So F to A, well that's B. A to B, well that's A. And then B to E, well that's going to be minus 3B. Because we knew that E to B was 3B, so going in the opposite direction, B to E, that would be minus 3B. Tidying that up, we've got B minus 3B. Well, that would be minus 2B plus A, and that would be equal to A minus 2B, because we prefer to have the positive vector at the start. Okay, so then we've got the question B to C. So again, B to C is this line here. We don't have a vector that defines that line, so we're going to have to take an alternative route and make one up. So we could go B to E, E to D, and then D to C. So again, I'll write that up. So B to C, well, that was B to E. Plus E to D plus D to C. Again, we know this is right because we start at B and we end at C, so B to C. Well, B to E, we've just talked about that, it will be minus 3B. E to D, well that's A. Then we've got D to C, which is plus 2B. Again, why is it plus? Well, that's because D to C is 2B, and we're going in that direction, so it's a positive. And again, tidying that up, minus 3B plus 2B, well that's minus B plus A. And we prefer to have the positive vector at the start, so A minus B, like that. Then we've got the question F to C. So F to C. So we have a look. F to C, well that's this route here. The problem we've got is we've got vectors that define F to A A to B, but we haven't got one for B to C, so we're going to have to find an alternative route. How can we do that? Well, we could go F to A to B, then we could go B to E to D, and then D to C. So it's basically the route. It's the combination of these two routes, F to E, and then E to C. So it's kind of a combination of those two routes, realistically. So again, I'll write it out. So we're going F to A, plus A to B, plus B to E, plus E to D, plus D to C, sorry. So quite a long route. So F to A to B, B to E to D, and D to C. So F to A, well that's B, plus A to B, that's A, B to E, that's minus 3B, which we've talked about. E to D, that's A, and then D to C, that's 2B. So again, tidying this up, so we've got B minus 3B plus 2B. Well, B minus 3B is minus 2B, and then plus 2B, well that's 0B. So I'll just write 0B. Then we've got A plus A, which is 2A. So our answer there is just 2A. Okay, and then I've got one more question I want to do, so I'll write that over here. And that is D to A. Well, that's D to E to B, and then B to A. So D to E plus E to B plus B, B to A. Well, D to E, that'll be minus A, because E to D was A, so going in reverse is minus. And we've got E to B, well that's plus 3B. We've got B to A. Well, A to B was A, so in reverse B to A, that will be minus A. Underline my vectors there. And tidying that up, we'll get minus 2A plus 3B, and that, with our positive vector written first, is 3B minus 2A. A question. So it says that OABC is a parallelogram. OA is represented by the vector A, so this part. OC is represented by the vector C, so this part. M is the midpoint of BC, so M is the midpoint of this part. And N is the point on OB, such that O to N to B is in the ratio 2 to 1. Okay, so what does all of that mean? Well, firstly, we've got a parallelogram. So we've got two sets of parallel lines. These parallel lines have the same length. So we've got the line O to A, and that's parallel to CB. So therefore, we must know that CB is also represented by the vector A. And similarly, OC and AB are parallel and have the same length. So AB must be represented by the vector C. Okay, then it says M is the midpoint of BC. So we know that if the whole of C to B is represented by the vector A, well then C to M is going to be half A, and we'll come back to that later on. Then the third thing we need to know is this ratio. So O to B is 3 parts. So O to B is 3 parts. And then it says O to N and N to B are in the ratio 2 to 1. Well then O to N must be 2/3 of that line, and then N to B must be 1/3 of whatever O to B is. Why is that? Well, because of this ratio. So we add the ratio together, so it's 3. So O to B overall is 3 parts, O to N is 2/3 of that, and N to B is 1/3. Okay, so then we have the following questions. So find the expressions for these vectors, giving the answers in the simplest form. So O to N is our first one. So this is a slightly different question, but they're quite common. We'll see a lot of questions like this, and you will when you're revising and looking through textbooks or past papers or whatever. Okay, so O to N. Well, O to N, so that's this part here, but we don't have a vector that defines that, so we've got to find an alternative route. How will we do that? Well, we know that O to N is 2/3 of O to B. So if we work out what O to B is and take 2/3 of it, then that will give us O to N. So O to N is 2/3, so writing mathematically what I've just said is 2/3 of O to B. So we need to define a path using vectors from O to B. Well, how do we do that? Well, it would be 2/3 of O to C plus C to B. So where did that come from? Well, we need to get from O to B, so we'll go that way and then that way. And if we take 2/3 of that, that will give us O to N because of this ratio that we discussed earlier. Okay, so 2/3 of O to C plus C to B. Well, that will be 2/3 of C, because O to C is represented by the vector C, plus A. Like that. So that's our answer. So O to N is that. And again, we haven't seen anything like that, but more and more vector questions will have questions like that. Okay, so then O to M. Well, O to M, we've got vectors that define that path. So to get from O to M, well, we need to do O to C plus 1/2 of C to B. Why is it 1/2? Well, because M was the midpoint, so it's half of this line. So if we take the halfway point, that will give us M. So then that will become O to C plus C to M. Well, O to C is the vector C. And then C to M, well, that's 1/2 of A. So it's plus 1/2 of the vector A. So that's O to M sorted. Then we have A to N. How are we going to define a path for this? Well, we're starting at A, so we've got to go from A to O, then O to N. So writing that down so we can go from A to O, and then adding on O to n. And how will we do that? Well, we know that O to A is the vector A, so going in the opposite direction, so going in reverse, is minus A. So A to O will be minus A. Then we've got O to N. Well, we already worked O to N out, and we knew that that was 2/3. So it would be 2/3 of C plus A. So then all we need to do is simplify this, so we get minus A, underline that, minus A plus 2/3 of C plus 2/3 of A. And then we've got to do 2/3 minus 1. So we're doing 2/3 minus 1. So it'll be 2/3 minus 1, and that will sort our A's out. So then we're left with 2/3 of C minus 1/3 of A. Like that. So that's sorted A to N. And I'll come across here for A to M. So we're going from A all the way to M. Well, how do we define that route? Well, again, we'll be going from A to O. Then we've got to go from O to C. Then we've got to go from C to M. Well, A to O, as we've previously discussed, is minus A. O to C, well, that's just the vector C. I'll underline my vectors as well. And then C to M, well, as we discussed earlier, that's a half of A, so it's plus a half of A. Again, we've just got to simplify and tidy that up. So sorting the A vectors out, we've got half minus 1, well, that's minus a half, so it's C minus a half of A. And now we're going to look at part 2 of this question. Show that the points A, N and M all lie on a straight line. So this is the second part of this question. So it says, show that the points A, N and M lie on a straight line. Well, what does that mean? It means that it wants us to work out and show that the line I've just drawn here is indeed a straight line. Well, how are we going to do that? Well, to get us started, I think if we look at the vectors A, N, so A to N, the vectors that define A to N, sorry, and then N to M, and then if we compare them, we might see some sort of relationship that will indicate whether it's a straight line. Okay, so A to N. So we just worked that out, but I'll just write it down. So it was minus A, and then it was plus 2/3 of C plus A. So it was minus A, oh, underline my vectors as well, plus 2/3 of C plus 2/3 of A, and then that is, of course, 2/3 of C, 2/3 C minus 1/3 of A. So that was our vector, or vectors that defined A to N. So then we've got N to M. Well, we're going from this point, so N to M. So how are we going to define that? Well, we can go from N to O, then O to C, and then we've got to go from C to M. Okay, so enter O. Well, from the work that we did previously, we knew that O to N was 2/3 of C plus A. So therefore enter O will be minus 2/3 of C plus A. To be minus 2/3 of C plus A. Then we've got O to C. Well, we know that that is C, so that's fine. And then we've got C to M. Well, M was the midpoint, and we knew that this line here, C to B, was represented by the vector A, so it was plus a half of A. Okay, so then we've just got to tidy that up. So we've got minus 2/3 of C minus, so watch that, it's minus times a plus, it's minus 2/3 of A plus C plus a half of A. Again, we just need to tidy this up really, so we've got, so for the C's we've got 1 minus 2/3, so that is a third of C. And then tidying up the A's, well, we've got minus 2/3 plus a half, so plus 0.5, and that is minus a sixth of A. Okay, so now we've got these two vectors over here, so we've got AN, so A to N is 2/3 of C minus 1/3 of A. Then we've got N to M, so the vector N to M, which is minus a third of C. No, sorry, it's positive, so it's a third of C, sorry, minus 1/6 of A. So is there a relationship between these two vectors? Is there a number we could times N to M by, say, to give us A to N? Well, we're not sure. So we have a look. Well, what about if we timesed N to M by 2? So if we timesed this whole thing by 2, well, we'd get 2/3 of C minus 2/6 of A. Well, that's 2/3 of C minus a third of A. And what we've just worked out here, well, that is the vector A to N. So therefore, we can write that AN, so AN is equal to 2 lots of NM. So this is difficult and it requires a lot of knowledge of a lot of different things. It's a difficult question. So what we need to recall now is that if we have two vectors that are parallel, so two vectors that are parallel, they are multiples of each other. So these A and N to M are multiples of each other. So therefore, they must be parallel. So I'll just write parallel. But the thing that makes it a straight line, because obviously if they're parallel, well, we're thinking, well, they must look like this, so like train tracks. They are parallel, but they share the common point N, so they both pass through N. So because they both pass through the same point, therefore, they must lie on a straight line. So therefore, they lie, so write that out, they lie on a straight line. So on a straight line. So to recap, why is that? Well, we looked at the vectors for a to n, and we looked at the vectors for n to m. Then we got, for a to n, 2/3 of c minus 1/3 of a, and n to m was 1/3 of c minus 1/6 of a. They're multiples of each other, so 2 lots of n to m is equal to a to n, and if we've got multiples of vectors, then that must mean that they're parallel, and because they both pass through n, so they both pass through n, well, they actually lie on a straight line. And then points that lie on a straight line are called collinear. So this point n is collinear, so it appears in both a to n and n to m. So we're going to look at another example, another exam style question to finish the video off now. To finish this video off, we're going to have a look at an exam question. So this was a past paper exam question. So it says that OAB is a triangle. O to A is 2a. O to B is represented by the vector 3b. It says find A to B in terms of A and B. Okay, so we'll go back to what, well, we've just built up really what we've done before. So we want A to B. There is no path that defines A to B. We've got no vectors that represent that. So instead we'll have to take an alternate route. So we go A to O, because we've got a vector for that, and then O to B, again, because we've got a vector that represents that. So I'll just write that down. So we've got AB, and that's represented by A to O plus O to B. Well, A to O, that's going to be minus 2a. Why is it minus 2a? Well, because O to A was 2a, so we're going in the opposite direction, so we're going this way, so it'll be minus 2a. Then O to B, well, that's simply just 3b. Just add 3b on. So that's our answer, minus 2a plus 3b. Okay, and then it says P is the point on AB, so this is the point, such that A to P to P to B is represented by the ratio 2 to 3. So again, what we'll do is we'll add this ratio together, so we get 5. And if we know that the whole of A to B is represented by 5 parts, well, we know that 2/5 of that will be AP, and then 3/5 of that will be PB. So like so. Okay, so we want to show that O to P is parallel to the vector A plus B. So we need to define a route for O to P. So in order to define this route, well, we can go from O to A, and then we'll have to go from A to P. Can we do that? Well, we know that AP, from what we've just talked about, is 2/5 of AB. And we've just worked out a vector to define AB. So we can do that. So it will be O to A plus 2/5 of A to P. Sorry, A to B. Because the 2/5 of A to B is AP. So I'll just write that over here. So 2/5 of AB. Well, that is AP. So similarly, this question doesn't ask, but if we wanted PB, that would be 3/5 of AB. Yeah. Okay, so then we've just got to fill in the blanks with our vectors. So O to A, well, that's defined as 2A. And then we've got plus 2/5 of AB. Well, we just worked out what AB was. So it'll be plus 2/5 of minus 2A plus 3B. Like so. So now we've just got to tidy this up, and then we'll look at the statement. So we've got 2A plus, well, 2/5 times minus 2A. Well, that actually isn't going to be a plus, is it? That will be a negative. So it will be minus 4/5 A. So you've got to be careful with that. It's a minus times a plus, so we get minus. And then it's 2/5 times 3B, so it'll be plus 6/5 of B. Again, then we'll tidy that up. So we've got 2 minus 4/5 of A. Well, 2 minus 4/5, we assume that it was a calculator exam, so we just bang that into our calculator. So 2 minus 4/5, well, that's 6/5. So 6/5 of A plus 6/5 of B. So that's sorted OP out. That's sorted. And then it says, show that OP is parallel to the vector AB. So we want to show that this here, what we've just worked out, is parallel to A plus B. So from the last part of the video, what you should remember is, so vectors that are multiples of each other, so I think I'll just write this down, so vectors that are multiples of each other are parallel. So I'll just write that there. So vectors that are multiples of each other are parallel. Are A and B and 6/5 of A plus 6/5 of B multiples of each other? Well, yes, they are. Because to get from A, we times by 6/5, and to get to B, we times by 6/5. So therefore, just drop another layer onto this. There you go. There we go. So therefore, OP is equal to 6/5 of A plus B. And from the statement I've just typed out there, vectors that are multiples of each other are parallel. So therefore, they must be parallel. And that's the end of the video. So we've ended with some quite difficult topics there, really. But we've looked at defining paths with vectors. We've looked at parallel vectors. We've looked at straight lines. So yeah, really take away what you've learned. And I would suggest to try some more of these questions just to see and check and consolidate your knowledge. So thank you for watching.